So we're learning techniques to solve this kind of second-order inhomogeneous ODE. And I said that the best thing to do is to, when you're trying to find your particular solution, to try to match what this function is. So there's one important case that I haven't discussed yet, and that's going to be the case we want to focus on most, which is what if f of t is trig functions like a cosine or a sine. How to handle that? Well, it is possible to make a guess for your particular solution which involves cosines and sines, but there's a trickier way, a faster way, which I want to teach you. And so before I get into this, which is what we'll need when we discover when we discuss the driven harmonic oscillator, I want to teach a different technique for this problem and also other problems, and that's a technique called complexification. It's kind of a funny name because it makes it sound like you're making the problem harder, but you're actually making the problem easier. So it simplifies certain problems. And let me give the schematic idea of how it works. So suppose you've got some problem involving a real variable, so a real variable, and trig functions like sines and cosines. And you're trying to find the solution to solve for this function. And so normally you would say, oh, let me just go this way, let me try to solve it. But maybe this is hard. So it's hard to do it directly. So then I'm going to advocate a different approach. It's just kind of it seems roundabout, but it actually ends up making things easier. The first thing you do is you complexify the problem. So I complexify to a problem involving complex variable like let's call it z, and exponentials. It's like e to the I something. So I'm not going to try and solve it as written. I'm going to first change it into a different problem, which is involves complex variables, and instead of trig functions, I'm using exponentials. So this is the what I'm calling the complexification. Now maybe this one is maybe easier to solve. So I'm going to solve it this way. And I've got now the solution. Oops, let's do black. Solution for, let's say, some complex variable z. And this one here is going to be easy, or easier anyway, maybe not easy, but easier to solve than the solution for x. So, and then once I have my solution for x, or for z, sorry, I now go back by taking the real part or the imaginary part to get x. Okay? So the idea is that basically it's hard to go this way. Solving directly is a little bit of a pain. So you go roundabout. You make it into a complex problem involving complex variables, and that is easier to solve. So you can solve for the complex variables, and then you take the real or the imaginary part at the end and go back to getting x. So you're going this way, sort of roundabout, is easier than going directly down. Okay. Okay, so let's do an example. I'll show you a situation where a couple situations where this can help you. So let's do an example of complexifying an integral. So let's do this integral, e to the x cosine 2x dx. Maybe you've seen this integral before and you've learned how to do it, and it's actually kind of hard to do it. You need to do integration by parts twice, And then you also need some extra trick at the end in order to do it. So it's kind of hard to do it as written. You can do it, but it's a pain. So what I'm going to do is I want to do it a trickier way using this complexification. So I'm going to instead examine a different integral. I want to examine the following integral. Let me call it IZ, meaning it's a complex integral. E to the x, e to the 2ix dx, which is the integral of e to the 1 plus 2I times x dx. Okay, why would I want to do that? Because if you think about it, the difference between these two integrals is this one has a cosine 2x and this one has an e to the 2ix. So this IZ, if I write it out, is two integrals, e to the x cosine 2ix plus e to the x, there's an I here, times sine of 2x. Sorry, there's no I here. Cosine 2x, sine 2x. dx, dx. Okay. To go from here to here, I used Euler's formula. E to the I theta is cos theta plus I sine theta. So you see, this thing here is exactly the integral I want to do. And then there's another piece to it which is imaginary, which is this second piece here. So what you can see is that the original integral that I wanted, I, is the real part of IZ. So I constructed a complex integral which has the integral that I wanted as its real part. And it turns out that the complex integral is much easier to do. You can see this thing here is a very easy integral to do. Okay. So we did the complexification. So this part here is the complexification. I found a complex integral which has my original integral as its real part. Now I will solve it. So we'll take IZ. This integral is easy to do. E to the 1 plus 2I x dx. Nothing could be simpler. It's just 1 over 1 plus 2I e to the 1 plus 2I times x plus a constant. Okay. So that integral is very simple. I didn't have to do integration by parts or anything. There's a very simple u substitution to do that. But that's not the integral I want, right? That's a different integral. So now I need to go back to the real part. And so for that I need to now take the real part. So the original I that I want is the real part of IZ. Now this gets a little bit messy. I got to take the real part of this, 1 over 1 plus 2I e to the 1 plus 2I times x plus a constant. All right, so a little bit messy. You got to do some algebra. So you've traded off a terrible integral for some like a little bit of a pain for algebra. So we've got to do some algebra here. So let me kind of go through it a little quickly. Okay, so what I do so far, I've got two pieces here, e to the x and e to the 2ix. So I took my e to the x is staying there. And then my e to the 2ix I wrote as cosine 2x plus I sine 2x. So this whole piece here is e to the 2ix. And then the prefactor out front, which is this piece, all I did is I multiplied the top and the bottom by the complex conjugate in order to get that complex number out of the denominator. Okay, so I'm out of room. Let me go on to the next slide. So I've just grouped together what we had on the previous slide, and let's keep going. Okay, so what am I going to have? 1 minus 2I The denominator here is a number times its complex conjugate, so I'm going to get the real part squared plus the imaginary part squared. So 1 squared plus 2 squared, so it's 5 times e to the x. This part stays the same, cos 2x plus I sine 2x plus a constant. Okay, I got to group together the real and the imaginary parts. So I'm going to take the e to the x over 5 out in front here, and then I'm going to have 1 minus 2i times this part again, cos 2x plus I sine 2x plus c. Okay. Okay, now let's figure out where are the real parts. Real parts come from this term, which is the real parts multiplied together, and then this term, which is the imaginary parts multiplied together. So I'm going to have here the real parts multiplied together gives me cosine 2x. The imaginary parts multiplied together give me minus 2i times I, that's plus 2 sine of 2x. And now let's think about the imaginary parts. The imaginary parts are going to come from the cross terms. The real part times the imaginary part here, and the real part times the imaginary part here. So I'm going to get I times sine of 2x and minus 2 cosine of 2x plus c. Okay, now take the real part. This is the real part here. This is the imaginary part here. So if I want the real part of this whole expression, I just ignore the imaginary part. And we can say that the real part of c is some other constant. So I'm going to get here I is equal e to the x over 5 cos 2x plus 2 sine 2x plus some other constant, let's call it c2. And I just ignored the imaginary part because I only needed the real part here. Okay. So there's an example of doing that integral. We did this integral here without doing integration by parts at all. We made it complex first, did the integral, and then took the real part. I traded off my integration by parts for a little bit of algebra, but I still think this way is easier. Let's do another example, which is going to involve ODEs.